Yeah.
Yeah, almost 30
deep.
deep.
It's pretty popular, honestly.
That's a good one.
Average view time.
30 of us
So when you're
desperate
just like,
enough to respond.
Skip to the section
Yeah.
where you watch.
This is my corruption.
It would be funny if a lot of them worked from our class.
We should do that. You know how you can take a bunch of Harvard classes on YouTube? You should do that.
Why?
You ever watched a Harvard lecture on YouTube?
No.
Well, there's a bunch of Harvard classes that you can watch on YouTube.
yeah, they're unreal.
Yeah.
I couldn't follow the first time.
Like, I watched a couple calculus ones at one point because I was confused on some stuff. Watched them and was like, am
Now
I even
more
in the same
confused.
class? Or we learned.
Yeah, like I was confused on Taylor Series, and they're going over like how to like actually like derive the actual like Taylor Series itself. Like, no, I don't. I'm gonna. So bad.
The Harvard Online Business School.
Bad.
What?
The Harvard Online Business School.
Would you play that?
Well, after you have to work, pay for it. Like I said, once you graduate from Harvard,
So did Tyra Banks, so it's not that impressive.
what you
Joe, grab
graduate
me one.
for? That's
Yeah.
One of those sheets.
No, the business thing.
Any online class.
Yeah, Tyra Banks
Don't
has
do
a
it.
business degree
Don't
from
do it.
Harvard.
Trust me.
Mine out.
A couple other celebrities.
You know the one that's like in terms of the modeling?
Yeah, American
He's
Icon
actually a
Models.
pretty
She's kind of badass.
I've listened to her talk about stuff.
I mean, not like I
That's like saying LeBron James doesn't understand business. I think he's doing
Well, I
pretty
can
well.
like tell
That's
some
he's
money
got
like
big companies and stuff.
pretty much. I said a whole bunch of
He's not just good at basketball. I think he actually goes to
No, like, I mean, yeah, I was like,
My girlfriend goes in and say, yeah, you see him walking around all the time, and like,
I do
there's just like eight classes in there. I think it's one class in like the office in
It's still taking, like, he's still taking a class.
He's the whole reason they have a rule that you have to play college basketball before joining the NBA.
Yeah, he's still great.
They were like,
Is this thing what we gonna get today? Yeah, this is it.
Yeah.
Numbers. So it's now. So should I like grade the attendance of this class for 10 points? Sure. I'm here. I don't care.
I have to give
My
you
whole
a
group
proof that
definitely seemed like the last class was a little
they just have a lot more people. Or
It-
is less?
It was maybe only one other row was filled up.
Someone told me that Antonio told the class that you wouldn't get lecture in lab. You wouldn't get points in lab if you like did go to class. Like any point.
Yeah, we can't see you go 0 if you don't show up. I kind of told people it's no biggie if you don't show up, but like if your group has problems with you or you don't perform well and your group calls you out on it, we have the opportunity to give you a 0 and your group can redo your part of the lab or whatever and get better points. Because you don't.
Hey, you format things.
Tyler was here, but he wasn't really here.
Like if you don't show up, that's kind of the opportunity you lose. If you're kind of sucking and your group calls you out on it, you don't do better. You get a 0. And then you fail.
And last time when I printed off a list of samples, it was wrong.
Because there was missing samples.
Definitely prints off right there. And then a big stack.
No. Oh my god.
Just pass it out to the whole class. Close
Alright.
the door.
Alrighty, so how was
We are large.
Lab 2?
Great.
Much better than the first one.
Good.
Oh, okay.
How was exam 2? Or exam 1?
Two?
Well, okay, great.
Did I
Let's say yeah, Phil.
Oh,
Exam 1. Everyone, 100%?
Yes.
No. Come on. 80%?
95.
Oh, I got an
No, they're not
80.
great.
Totally bad.
I have definitely thinking like a 73.
I'm just letting you all know if the average is very high, the second one will be very hard.
How are we supposed to
He
know?
already told us
the
the second one was
going to be terrible.
I mean, if the averages are fair or low,
Yeah.
it will not be that hard. But if the averages are very high, the second exam will be very hard. So you will have to study really hard.
Let's hope a lot. He already told us the second exam.
I doubt a lot of people failed the first one.
Hundreds and zeros. Just split the gap.
I'm guessing the average is going to be above 80. So that's the second exam will be very hard with an average probably around 65. Would be my guess. That's how he's going to distribute the class. So.
How many people on
Everybody
average
back in
don't
their
have to
place.
take final?
Yeah, you thought you were good at things, but that exam thing came around.
So about half.
Is it? Does he just average your two and then? Okay.
If you did well enough on 2, he thinks you understand the class enough to not take the final. I've had people people that grade go slightly up, maybe half of that grade was like taking it. But it is nice not taking it all up, right? To be honest.
Well, as of now, we have 2 other exams that day.
Let's
Or
get
some
stuck.
things.
I think Philip, all you do is say something to me. He let us take ours the last day of class. Phillips. But then again, we like haggled within the semester before for that opportunity. So, but he couldn't have a problem with it. All right. What do we know about steel microstructures? Made of metal. Okay.
Ferrite, pearlite.
Ferrite, pearlite, bainite.
Marcasite.
Good. Maybe. Probably not the case. What else? Martensite?
How do you get different phases?
Or
Cooling or composition, right? And what's the major alloying element? Carbon. Good. So what are the major tools that we use to try to figure out what we have in our steels?
CCT or face diagram.
Three of those are perfect answers right there. By the way, everyone will probably be involved some point in this class. I was definitely calling people out, spreading it out, making people not answer questions and people answer questions.
What was the third one?
Turn around. No, turn around. They're all right behind you. We're going to be using them today. So.
So this one is basically going to be very similar to your lab 1 in 3333.
Use your tools. That's how you will get a good grade on this lab. Right?
Are you sponsored by Dr. Phillips now?
Getting a little bit from that book recently.
Source internet.
Sample 1. What do we think our carbon content here is? Take a guess.
Do you have a handout?
Nope. I'm calling on people today. This is how it's gonna go. Everyone's getting involved.
Very low.
Yes. Commercially pure. So it's almost 0. There's no way you can get 0, to be honest. Actually 0. Pretty much impossible. So, what does that mean our phase is present? And we'll go with Tyler. What phase is present?
In the commercially pure.
Yep, the one on the screen. Or you can use that diagram behind you.
I'm gonna
Or
say
Or on the back of your paper.
something soft like ferrite.
Okay. Anything else?
Maybe perlite.
Try again.
You see.
Oh wait, no, I can't have cement. I don't know.
But I just said it's not 100% rid of it. So what would that be? 0.5% of something be? Huh? No, definitely not probably. Impurity elements.
Okay.
Okay, good answer. So what do we think the white is, Tyler?
Ferrite.
Good. What do we think that black cluster in the right-hand corner is?
Impurity elements.
Good. I like it. I might call on you later, I might not.
So for these samples, or for this lab, you're going to introduce the things that you're using in this lab, the tools that you're using in steels, right? When you're going to see like how much we use all these, but you are going to need to put these different phase diagrams or these different diagrams in an appendix. That way you can refer to them like multiple times and plot all of the samples.
So step 1, we're going to put them in the intro and introduce them. Not with all your samples on there. Just as the phase diagram. What is it? Talk about it. What is the hardness versus carbon content? Talk about it. Then in the appendix, we're going to put a whole bunch of plotting on them where you're actually going to use them and reference them in your appendix. It's like figure 18 or 19. Alright? We got the gist of that? Good. So, what?
This first section is just about different compositions.
So, what diagram are we going to do to look at the cooling path 8 for this first sample?
That one? The CCT?
You sure?
Well,
It wasn't
that's
welded.
just plate metal, isn't it?
Yep. it's going to be equilibrium cooling. So phase diagram is your equilibrium cooling. So we're going to use that one. So that means when you plot it, we put a nice big line from liquid all the way down where the composition would be based on your carbon content. Kate, what's the carbon content of this one?
Close to 0.
There we go. It's pretty much the left-hand side of your graph there. The back. Alright, so what other tools can we do to verify that we have ferrite? Max.
Hardness.
Okay. On that graph?
Yep.
What's the hardness?
The hardness is going to be, well, it says, that's actually Rockwell C.
So what would that
This
mean?
is Rockwell B.
You can still use it.
It's low.
It's going to be way low
It's going to be
compared to Rockwell C.
way low.
Yes, correct.
I don't know.
There's a converter online, so it's actually plotted on Rockwell C.
Okay.
Also, the graph is provided on Bernoulli on the other side, so you can just convert them all to Bernoulli hardness, and it'll plot the correlation the same. So it's very soft. So that's our second tool that we use to show defense on what's there. Everyone got that? So what's on the grain boundaries, Andy?
Probably a little bit of carbon precipitate.
Sure.
Yes.
You can only see them because of the edging. Your period elements are very small. It's only going to be seen in those clusters. Show you whatever. You can only see the grain boundaries because of the edging use. That's it.
But if it's
So I'm hinting, do not label the grain boundary and say there's impurity elements there. Please. That is wrong.
any questions?
Any guesses on what type of impurity elements are there? Daniel. Not an impurity element. Try again. That could be it, but more likely phosphorus, silicon, and manganese would be your impurity elements present. Not carbon. That's not an impurity element in steel. Sorry. By the way, if anyone wanted to be impressed, Lippa was in here and saw this and knew what it was just by the picture. Just putting it out there. I was kind of impressed.
This isn't steel. This isn't steel, man. This is iron. Iron, not steel. You guys know the difference?
Because there's no carbon in it.
So,
Right?
right, yes.
There we got it.
Does anyone
Cool.
need more explanation? Yes, no. Right, so iron, this is a pure element with carbon means it's steel. Okay. Alright. Any questions on is this everything?
Yeah.
Any questions?
So hold on. What do we need to provide for the lab report?
Point out the
Point out the phases and then how you got to know which phases are where.
Good. So how many pictures should we need? Thank you. Thank you. One picture.
point out the impurity element.
Yeah. That big black cluster. Now you're good.
So,
Everyone see them? Good. Good. Alright, that's pretty much it. Use your tools, make a fence on what's there. Got it?
why? Yeah.
Don't just say this is here. That's it. This is here because of the phase diagram, hardness content,
Composition.
composition. Here we got it. Good. Example. What is the carbon content of this sample? I called someone out, so don't just shout it out. Good. Good answer. 0.6.
Does everyone know how we got to that?
How do we know that?
Yes,
Good.
1060.
It's in the name. Alright, so of that, just by the carbon content and knowing that it's equilibrium cooling, what do we think is present based on looking at the phase diagram? Phase diagram, not just look up there.
I'm just looking at it anyways. I haven't seen it either.
Phase diagram behind you. Who wants to answer? Back row, one of you four. What do we think is there based on the phase diagram?
Ferrite,
And?
perlite,
Good.
maybe some cementite.
Really? You think so?
What?
Based, hold on. Based on the carbon composition, would there be cementite by itself? Let him answer.
No.
Why?
It's not far enough over.
eutectoid point. That's how you're able to tell. So yes, what you said was correct. Good. A mix, but you can, it's not. You can also get just cementite and perlite.
So
Does that
perlite.
make sense? If you're on the other side of the eutectoid point.
So perlite's as Philip says, it's a microconstituent, and not technically, it's not a phase, but it's made up of ferrite and perlite. Does anyone remember the hardness of ferrite compared to the hardness of perlite compared to cementite?
Good.
So you guys said
Speak up, Max.
Yeah.
Say it again.
Cementite's really hard. Perlite's in the middle, and ferrite's really soft.
Good. Ready? Hold on. Tell me where the ferrite is, where the perlite is, and how they form.
Using a phase diagram.
Yes, using the phase diagram. That's the hint. That will easily give you an answer.
So like when you're doing these samples, you should be able to walk us through the phase diagram and
I don't know what that
explain.
is, so please introduce it into the intro.
What?
I didn't call on him. I'll call on you.
Is the ferrite at the boundaries and perlite grains?
Good.
So how relate that to the phase diagram?
Okay, so as it goes from austenite to ferrite, austenite grows in the grains, and then once they form, perlite forms at the grains again, and then
So grain boundary ferrite grew first.
From fully austenitic steel.
Fully austenitic steel, you go down into the two-phase region of ferrite and austenite. During that is where you get your cooling rate to form ferrite on the grain boundaries. Once you get past the A1 temperature, then you will go to perlite.
Yeah. So all of the austenite you have just forms perlite from there.
Instant, bam. Well, not like instant, but in our imagination, instantly.
Yeah. It's pretty close to the eutectoid temperature. So it's pretty close to it.
So Kate, what do we think we need to include in this for your lab?
The phase diagram, and it gave a hardness point, so a hardness.
Okay. And
Since it's equilibrium cooling, you just draw the line straight down the phase diagram.
and
A picture.
good. A picture.
I
Good.
thought that was
One
good.
picture.
Right. And you can kind of see the lamella of the perlite in the middle of the grains. So you
Who
can
knows what that is?
kind of see that.
Andy.
Just the layers of
Good.
perlite and cementite back and forth.
There.
Oh, I'm sorry, yeah, ferrite.
Good.
There.
Would you call those subgrains?
No.
No. Not. That is not correct.
Why are they not? Does anyone know why they're not solidification subgrade methods?
Because they don't solidify.
They don't solidify yet.
It's your mixing of cementite and
Yeah, it's a
Ferrite.
so the
That's what it
solid
is.
state phase transformation. So it's going from one solid phase to another solid phase, and it has nothing to do with solidification, which is liquid to solid phase. So solidification happens up there at the 1500 degrees C area, and then anything past that does not have to do with the solidification stuff either.
So that happens when you form austenite.
Yeah. No. It happens. What's the first phase that forms when you're
Hold on.
cooling?
let's call somebody out. You. First phase that forms upon cooling. Okay. Around what temperature does it
Delta
start?
ferrite. Delta ferrite.
Up 1500,
Yeah.
It's a little higher than 1500. Yeah.
well, yeah.
Good.
5130 something.
35.
This is good, and we're testing you on things you might need to learn. Put it out there.
So that is when you get your solidification structure, solidification subgrain structure, and then from there when you turn to austenite, that's a solid state transformation. Okay. And then again, you get another solid state transformation from austenite to ferrite or perlite or ceolite. Okay. But yeah, any questions on this one? You can see the perlite structure.
The single picture that you want for this, you want a higher magnification so you can see those.
Do you want us to point out the lamella?
Yes.
Yeah, if you can see it. Or
It
at
should be
least state-
noticeable.
It should, yeah. You should be able to find one with a more clear, yeah, right here.
not, this will be on YouTube. Ask your friend for the YouTube channel we're on.
Alright, any questions?
Alright, next sample. 1080 steel. Okay, who's going to be the one to get called on now? Whenever you pick your head up, this is carbon content.
Oh. 0.8.
Good. Good answer.
Where would that be in your phase diagram?
Same person.
With respect.
Phase diagram.
With respect to the U-type.
Is it hyper?
Yes. Good answer.
Hyper-eutectoid alloy. What was the last one that we did?
Hypo.
Hypo-eutectoid. Good. Make that distinction when you're writing about them. And
Make
like,
it
at
clear you
least talk
understand
about the
that.
phase diagram.
Yes. Alright, so hold on. Who are we gonna call on? Person behind Daniel. Yes.
Daniel.
Oh, you're gonna Daniel. There we go. Alright, what do you think is there?
Perlite and
Pretty good answer, man. Spot on. Alright.
So why does this look different than the last one that we just did? They're pretty much on the other side of the. This one's actually pretty close to eutectoid steel, actually. Yes, instead of ferrite, you get the cementite that forms in that two-phase region. Does that make sense?
You're gonna have a lot more semen type than you did ferrite too, because of the angle of the transition line.
Are you sure?
According to the phase diagram, like the
But you see how close your composition is?
yeah, but they're
You're very, very close.
I guess the other one's about as close to.
0.6 to 0.8. The middle's 0.77. You
Well,
might.
it still looks bigger,
It's not
like,
that much.
on
It won't be that much. You're very close to what you technically look like.
But yeah, so explain how this forms based on the phase diagram, right?
All right. So based on the hardness, what do we think's there? The person next to Daniel.
gonna be more cementite that's harder,
More cementite than perlite.
or mostly perlite, but if it's harder than the last sample, there's gonna be more cementite.
Good. Using your tool in the back. Our hardness is 43 Rockwell C.
So
What's
you,
that tell us?
That there's some cementite making it harder.
Yes. You called that right.
yeah. That's not really useful right now.
I thought you weren't allowed to use that unless you knew you had markings.
Yeah, we don't know what.
So you know it's harder than fine perlite, pretty much. Right. Right. You can look at that. Still got to plot the point. Still got to plot the point. And then, okay, so the concept here is you actually get very small amounts of cementite, but it acts to increase the strength of your microstructure as like cementite precipitates. You really won't be able to see them because it's pretty much the same color schemes you're looking at.
You might maybe at the green one.
Maybe, but it's still not very easy to see. So you pretty much you need to say it's there. Okay, like that's how you know the hardness is higher than fine perlite. Everyone got that?
Yes.
One picture.
The reason you might see like light patches here. What is white in our carbon seals when we etch them with nitrile? Ferrite. Should we have any ferrite in this sample?
Yes and no.
So it's in the perlite, right?
So if you go across the perlite,
There you go.
So if we cut it, remember this is a 2D representation of a 3D structure. So if like the layers of the perlite are lining up with our cutting plane, you might see more ferrite in one grain.
Did you have a question, man?
My question was what was the etchant? But we said nitrile. So.
Yeah, I mean it's pretty much all nitrile. All right.
Any questions on this one?
homework comes into play now. You're gonna have to look the carbon content up for these last three on your own. I will give you some hints, at least make sure you don't have a completely wrong answer. But Kate, what do you have to guess based on what you see there in the hardness? Where do you think the carbon content would lie? You can also look at the screen. It would help you.
I was about to say, 'cause I don't see it in the list.
It's
HSLA
HSLA.
65.
Oh, okay.
Yeah, this is an HSLA sample.
92.
Very low.
Rockwell B.
So
There's not a lot of carbon.
that means
It's gonna be hypo-eutectic.
there's a one
Or
hint
eutectoid.
for what your carbon content should be. To the left of the eutectoid point. Okay? So what do we think we see based on me telling you that? And all these steels have been etched the same. What is the white? Kate. Good. What is the dark? Daniel, I didn't call him last time. The other Daniel. Good.
You might be able to see some of the lamella in here. I can see them when I'm looking like in the microscope. You can't really.
Some in there maybe.
Yeah. So it's kind of hard to tell, but you should be able to see them when you look.
Still talk about it though. That's the whole concept behind perlite. Plot them on your diagrams. Defend what you're saying. Everyone got the gist? Good. What do we? Hold on. What things do we need to do for the sample? Huh? What? Try again. How many pictures?
At least one picture.
What?
One picture.
One picture. And?
The
And?
phase.
You need to look at the carbon content. You need to use the phase diagram and hardness for all of these, so that should be a given. Alright.
Should we go out and find the phase diagram?
Really? Do you need to go find the phase diagram?
Well, plot it on.
Yes. You
Yes.
need to plot this on the phase diagram to represent your equilibrium pooling. Alright. So, homework again. We're going to look up the carbon content for the next sample. A 537.
This one's a little more in depth, so.
This will probably be a solid page of writing, just letting you want to know, because there's more to this sample. So,
Kate, that's yours.
we have a flame. We have a flame cut edge. Back row. What does that mean? Somebody in the back row that hasn't answered yet. I think the guy that answered left. So, back row, come on. Get involved. Flame cut edge. What would that mean? We had a heat input. So that means good.
Right.
And that means related to the iron-iron phase diagram. To get a heat affected zone, you have to be heated above A1. Right? Back to the Austin region. No, it's not just above.
Yeah.
It's not above A2. No. There you go. That'd be your intercritical region. Okay, so here we have the base metal. So what do we see? Back row that hasn't answered. A lot of it, right? Okay, what else do we see?
Anything? Or what?
So you see white ferrite. There's definitely something else on the screen.
You don't have to describe it in phases. Just what do you see?
What do you see? Dark wavy things. Yes, that represents a hot rolled structure. So that's how you. Yes, I believe it is.
Okay.
So are
Breaking it
those
down.
the grain boundaries then? They're just all stretched out?
No, they're not
Your
your
grain boundaries are those.
Oh, they're really small? Okay.
So, breaking it down.
Okay.
Relax. So, go back to the overview. So we need an overview picture to show you heat affected zones. Can everyone label those? I think we've done it multiple times now. How many regions are in your heat affected zone? 3. Good answer. Who knows what they are? Good. Do we think we can label those? We're going to go through them. Oh yeah, also. Good. Alright, so we'll zoom in to the base metal. bandings from your rolling of the plate, and that's basically your segregation bands.
The banding is actually from the. This is a carbon manganese silicon steel, and silicon prevents cementite from forming. So what happens is the carbon actually starts to band together like this because the silicon is preventing it in the lighter areas. Right? So because we have more carbon in these darker bands, what does that mean? We have
With an S.
oh no.
Oh.
Yes, it's because of segregation.
That's for your S.
No. But we should have perlite there,
No.
right? Perlite or cementite with the barite. As we move towards the heat affected zone, what are we noticing? This is the base metal over here. That side is the heat affected zone.
So we're at the intercritical region right now.
So smaller grains, I heard that. Why would we have smaller grains? Less time for grain growth.
In reference
But why
to
is
what?
it smaller than the base metal?
Because the heating process, dislocations are able to move in grain boundaries.
That's one reason, but it's more likely it's more because of the phase transformation that you see when we go up in temperature. So when it goes to austenite and comes back down as ferrite, when it breaks up into ferrite again, those grains are gonna like reform as like smaller grains. But it's not heated up long enough for the grains to grow. Does that make sense?
Good.
What else do we notice in this heat affected zone? From here
The dark.
to here. They're wider.
Right. Yeah.
Kind of. They're like fuzzier. Can you see that?
So what would the fuzzier mean compared to the not fuzzy side?
So from here to here. Does everyone see that?
I kind of liked his answer.
Diffusion. So why would we get diffusion? Someone explain what diffusion is.
Higher temperatures.
The plate was heated back up, and this is the reason that was affected. So
Yes. So it was heated back up, and then the carbon was able to kind of diffuse out. And it wasn't, so it didn't have enough time to kind of like segregate back out into what we see in the base metal, right? Okay, so as we keep going, what?
Does everyone understand how the banding was kind of getting going away? Okay. Need to talk about that.
And you can kind of see how it pretty much disappears once you're at this.
The coarse grain heat affected zone.
Alright, so where would that carbon go? In the solution to form.
No. Max.
It could be. But what does it
Could
look
be.
like?
It sounds like apartment stuff.
What does it look like? Martensite. Right, so we have martensite here, right? In our coarse grain heat affected zone.
How do we know it's martensite? Needle. Needle segregation. Good. These are great answers.
So the carbon, when you're cooling it, it's cooling pretty quickly, so it doesn't have time to segregate out into those bands again, and it'll get trapped in the martensite.
What about the hardness? Can we use that? Huh? But what hardness is given to you? Good. So please don't say defend this answer with the hardness, because that's wrong. It's the base metal. That's how you can defend that part. Okay? So you need to defend how you know it's martensite. 6 degrees, type of cooling. Get the gist of that. Segregation of the bands not being there. You know, carbon diffused into the solution. We know the white's ferrite, the dark is perlite. Everyone got, I think covering all the details here so everyone gets it all. So how many pictures do we need?
2, 3,
start with the overview. Always start with an overview because if you just jump right in, I'm not gonna. If someone was reading your sample and like didn't see the sample, you don't want them to just be very like they're gonna be lost, right? So if you're gonna show them a map of your sample, show them the zoomed out one, and don't put zoomed out or zoomed in your lab report. It's higher or lower magnification. Okay. Yes. Okay.
What magnification are we at right now? Good. Okay, so what pictures do we need? We need an overview, not Kate.
Martin side.
Martin site. Explain what? Yes, and so it gets fuzzy and changes. And we have to do one more thing for this part. What? No.
What's carbon content?
Yes.
And you can, I mean, if you want to do each separate region as a separate picture, you can do that. If you can do it, if you can do 2 regions in one picture, you can do that.
Alright.
As long as it's clear. And don't try to label the microstructures in the overview because we can't see them. Okay.
Unless it's all one.
Unless, yeah.
Technically could.
Yeah.
Like, in the first sample. You could just say this is all fair, right?
That's actually good.
But you're gonna be able to show us the impurity. Alrighty, so this is gonna be a challenge for everyone. After using all your tools, we're gonna make you figure this one out on your own. I will give you some hints. First off, you're gonna have to look up the carbon content. I'll give you a hint. It is less than 0.77. Okay? You get the gist? There are 2 phases present. Alright? We got that? Based on the carbon content, you'll be able to figure out which 2 phases are present and what to see. Alright, so this is a weathered steel. What is added to make weathered steels?
Or what is a weathered steel?
Yes, what is a weathered steel? Come on.
Does anyone know what a weathered steel is and what it's used for?
Yes, they have been outside for a while because that's the purpose of a weathered steel is to be outside and avoid corrosion.
The point of weathered steel is basically for outside structures, and so a weathered steel will actually like rust. It's intended to rust, and that's why you see a lot of the brown. Like if you see a bridge or like
Copper
something.
With
Yeah.
copper. Oh, so he talked about this in class and no one knew what it was.
Well, you call it weathered steel. Weathered steel. We're talking about copper.
Yeah. You add copper to make a weathered steel.
We just knew Cash is talking.
So we need to look up the carbon content. I want a couple sentences. What do you use weathered steels for? Look some stuff up. Give me a good old
Just
Google.
like one sentence.
Not
two
some wiki,
sentences.
please. I want to see copy from wiki. Put it in your own words at least. Okay. You gotta figure out what's there. You gotta defend it. I gave you 3 good hints, or 2 good hints on what you should be able to figure out. Alright? Use your tools. Give us cooled equilibrium. Have some, the hardness content. That's how you figure these out. Alright? Any questions for this one? Grad students, if you'd like to know what it is, stay after class. That's what I did for the other ones. Or figure it out on your own and come tell us the answer. Alright.
Any questions? How to figure it out? What tools you need?
Does everyone think they can figure it out? Back row, I saw some navies. Why don't you think you can figure this out? Huh?
Said I can figure it out.
Second to back row, yes? Third row. Can we figure it out? Second? First? Good answer.
That was my answer too.
Good answer right there.
Gave you something.
Alright, that's pretty much it. For me, now we're going to go over Genevieve. Come on.
Yes, I got A36 H2O quench.
Good, yes.
Alright, so these 2 samples are more going to be about your cooling rate. Alright. So what graph are we going to use now for some of these? The CCT.
Step 1. You have to look up the carbon content for A36. It is not a range like someone wanted to say in the last class. I looked online and multiple people sell it with about the same carbon content. So it's definitely an answer.
Alright, so what? This is water quenched, 836, and this has pretty low-ish carbon content. I don't actually know, but it's less than 0.77.
So there's a hint. Lowest carbon content. Yes, water quenched.
So what do we expect to see? Good. And what do we see here? Right, is it fully martensitic? There might be some ferrite at the grain boundaries. It's some of the white right here. Maybe right here, right? But if we go to the middle of the sample,
What do you think, Max?
do you know how there's a little more ferrite here in the middle? Can you kind of do that?
Let's call on somebody.
Do we need a picture?
Two grad students. Why do you think there'd be more ferrite in the middle of the sample? There you go.
Do we need a picture of the edge and the middle? Or just
If you want. Pretty sure we only talk about one thing. As long as you can find the two microstructures present, we'll be okay. Should easily be able to find them in one picture. Yes. You give me more than two, I might just start putting X's on them.
Alright. So what tools are you going to use to figure out what this is? Or to explain what this is? And what else? What? No. Yeah, for this first example. The hardness and the CCT. Good.
And you can't find a CCT exactly for A36. When you look at the carbon content, find one that has a close carbon content. It'll roughly be the same. Never got that? Good. By the way, you gotta reference stuff when you find it on the internet. You can't just
Can we source internet? Yeah, can we source the internet?
no.
Can we just put the link in, or do we have to like MLA
What do you think?
try to do it? Because some of it would be honestly harder to find if it wasn't just the link.
I mean,
No, you should just put it in UZViv or citation
yeah,
machine.
easy to citation. Click, done, it'll
Yeah.
tell
You
you
only
what
get
to know.
one ad for each.
Do you want MLA or APA?
What?
Easy.
Whichever one you
One
do,
ad
just make
free
sure it's
and-
consistent.
Okay.
You guys are plugging them. We'll tell them.
30 seconds.
I realize it today.
Is it okay that I cited the YouTube?
Easier just to learn how to
videos?
cite them.
In addition.
You're here now. So.
So for A36, for our air-cooled sample, what do we expect to see?
Not
Softer phases.
Softer
Such as-
phases.
Ferrite,
Open-ended.
ferrite,
pearl.
Alright, hold on, let's keep going. Why do you think there's softer phases?
Slower cooling.
No. Tyler's answering.
slower cooling.
Okay. That's it.
Yeah, I mean you have.
That would be about it. There's not much more to cause. So what's there, Tyler? And what's where?
You have flarite, and then you have perlite that nucleated off of the boundaries.
Which one was which?
The lighter is ferrite, the darker is perlite.
Looks pretty good to me. You see some of that banding? What's going on with structure? The perlite?
A little bit.
I hope so. Otherwise, it's really not
There
perlite.
should be some
Right there.
Oh, right here.
Yeah, that's a good. That right there is pretty good. Pretty much gotta use your tools. Defend it. That's pretty much all there is to this one. Just different cooling rate. Provide you with a different microstructure and different hardness. But you gotta defend why it's there. So how many pictures? Good.
This one.
No, there's no or two.
Alright, what do we expect to see in the furnace cooled one?
Hold on. What is a furnace cooled? What kind of cooling basically equilibrium.
So
So what would we use to prove out composition?
Phase diagram.
There we go. Good.
Alright. So for this sample, what do you notice? What do you see here? Ferrite. And more. Right. So the perlite might have more.
No.
No, there's not more perlite.
No.
The ferrite grains are larger.
That's what you're noticing. You're noticing the grains are larger. Why are they larger, Kate?
Because it cooled very slowly, so there was a lot of time for grain growth.
Money answer right there, people. Stuff to put in the lab report. What? What do you mean? Hold on, stop. Turn around. Look at your paper. What do you think it is? There's really like one answer you could have here. Huh? Yes. Do you know why? Once you cool down from your two-phase region of ferrite and austenite, everything else goes to perlite. But if you have a lot of ferrite present, what does it tell you about the carbon composition? Okay, so since we know that, why don't we actually do a tie line? Once you find out the carbon content, you can tell me how much ferrite you think is present. That's included that in your lab report, yes. Got the gist of what I just said? Good. Are we sure? I'm sure there'll be a group that doesn't do it. Even though I definitely said it. Obviously should be a fair amount. Or you can do what he said. He thought about making you guys like plot it out and do like the dot things. He wanted you to do that, but I told him
I
no.
said that was a possibility.
So. Okay, that's pretty much it for this one.
Yeah. Any
All right.
questions?
So Andy, what is the composition, carbon composition for this next sample?
It's 0.6%.
Here we go. We only have to look up how many carbon compositions? 4. Definitely 4. The last 3 and then that last one sample, yeah. Is the carbon comp going to change for the last sample because of how we cooled it? Good. That was a trick question.
Alright, what do we expect to see in the 1060 water quench?
More
steel?
martensite.
Martensite, cool. There's some patches of ferrite in here. Can you see the white patches in here? So like right here, that's ferrite. Maybe right there, that's ferrite.
So how does this compare to the last sample that was water quench?
No. Those are the needles.
This is less ferrite.
More martensite because it has more carbon content.
More martensite. Or rather, you know that there's more carbon content. So there's you'll look up A36 and you'll know that there's more carbon content in this one, and that's why you have more martensite, right?
It's also a lot harder.
And it's also good. It's also a lot harder, right?
We're using our tools to defend our answers. Stressing is pretty hard. That way this lab report's pretty smooth for everyone to make, for me to grade. Okay.
Alright, any questions?
This one is pretty basic. Alright, so what do we think the air tool is going to look like? Max.
The air cool.
Yeah, what do we think it'll look like?
You're going to have a slower cooling rate than the water quench. You're going to have a lot of ferrite.
Really? And 0.6% carbon?
0.6. Okay, well, you have some ferrite on the grain boundaries and then a lot of perlite.
Better answer. Is that how it looks like?
Yes.
Good.
Any questions?
Everyone get the gist of that one? Same concept. Use your tools, defend it. Are we going to use the iron phase diagram for this one? No, it's definitely a CCT. Okay. Good. Last sample for for the day. So what's gonna be? Hold on. What's gonna be the difference between this and the last sample? Not you. Let's go back row again. What do we think? Okay. So what should we see? Pretty good answer. I like it. Let's see what that looks like. Wow, that's wow. If you can find the spot again, that's kind of cool. That's your perlite band.
Wait, what is it?
No, I kind of answered. Sorry. I thought it was being empty. I've really never seen it look like that so easy.
What magnification is this?
This is 400.
So is that banding's only visible when it just happens to cut the grain in exactly the right spot?
Yes.
Same concept. Use your tools. You know, you're doing for this. You'll be doing a little bit of comparison for, you know, the different steels, like 836 for the water point. You know, do a little comparison between those. Then do a comparison between like 836 itself, between the three, and then 1060 between the three.
Grain sizes between the air cooled and the furnace cooled.
Right. Self-explanatory. Everybody got it. Grad students, if you'd like to know the mystery steel, you can stay after. I'll tell you. Unless you figured it out. The last class, the grad students figured it out on their own. Yeah. Don't shout out the answer either. Pretty much all you gotta do, anyways. Alright, free to leave. We're doing 5 minutes early. Everyone go to that line.
Yeah. Super easy. Just open up all three hard ones.
Yeah, I gotta remember. I was watching
How'd you do on the exam? Not good? You're above average? Close to average?
No.
Oh, well, that's right.
Yeah, it was like definitely what I ordered.
Really?